Hello again and welcome back, everyone. We hope you enjoyed the virtual networking session. Up next, the evolution of additively manufactured personalized implants is the topic of our next presentation by Alex Kingsbury, Additive Manufacturing Fellow at RMIT University. Alex leads the outreach and engagement for the RMIT Center for Additive Manufacturing. Previously, Alex was the director of CSIRO's Additive Manufacturing Innovation Center, Lab 22, and the research group leader for additive manufacturing. In these roles, she oversaw CSIRO's additive manufacturing research projects, both strategic and industry funded. She was also responsible for implementing a program of local industry engagement, the first of its kind in Australia. Alex has worked more broadly in metal technologies, including additive manufacturing since 2011. Specifically, her focus has been in the area of metal powders for additive manufacturing. Alex's volunteer roles include sitting as the independent expert on the Standards Australia Additive Manufacturing Technical Committee, Melbourne, Australia's Ambassador for Women in 3D Printing, and TCT Expert Advisory Board member. Welcome, Alex.
Thank you, Roxanne. Thanks for that lovely intro. And thanks so much for having me, everyone. I'm going to just share my screen here. We'll get started. Okay. So today I want to talk to you about the evolution of personalized implants. And I wanted to talk about it within the context of it being in Australia. Obviously, I am Australian. I come to you from Melbourne, Australia. This isn't about me being sort of like, woo, Australia, but it is a little bit about me at least being across the scene over a number of years, and also having been able to witness the progression of our approaches to personalized implants and how it's really developed over the short space of a few years. And I think it's a really interesting story to tell. And with regards to personalized implants, I suppose the language can change a little bit from time to time. We can use personalized, custom, patient-specific, but I'll take you through that as we go. And I think that there's a couple of good lessons learned out of what Australia has been able to do. And so I'd like to finish on that. So first of all, you know, why do we want to have personalized implants? Currently, if you receive an implant in a hospital, the chances are, very, very high chance, is that it is a standard implant. So it's a standard size. I've got one just here with me. This is actually 3D printed, and of course 3D printing produces standardized implants as well. But you know, if you need a hip replacement, and this is an acetabular cup, now the surgeon just goes, sizes up your anatomy, basically chooses the closest one that fits, and then will open you up in surgery, scrape out the bone that's required in order to fit this standard implant, and put that in. Now, the issue with that is that the surgeon is going to be scraping away a heck of a lot of healthy bone in order to accommodate that standard sized implant. And really, when it comes to surgery and removing bone, you don't want to remove healthy bone. That's not an ideal scenario, but that's the scenario we work with currently when it comes to standardized implants. The other thing about standardized implants, and particularly when they're conventionally manufactured, is that they tend to be a bit over stiff. This leads to stress shielding, which means that you've got an implant sitting up against healthy bone, and the stiffness, or the Young's modulus of the implant, is higher than the stiffness of the bone. And when that happens, you've got a hard, stiff implant up against some nice, soft, healthy bone. That soft, healthy bone starts to die off, and it doesn't accept the implant. What we want is for the bone to grow into the implant, but it'll only do that when there's a friendly surface nearby. So if we can match the stiffness of the implant to the stiffness of the bone, then you're going to get that bone ingrowth, or what's known as osseointegration, bone growing into the implant and accepting it. The other thing around standardized implants is that if the surgeon is has got you open in the OR and is scraping away healthy bone, they're actually spending a lot of time in surgery with you open to scrape away that healthy bone to put the implant in. Now, the longer a surgery is, the higher the chances of infection, the higher the chances of revision. And these are all things, and the longer the rehab for the patient. So these are all things that we want to try and avoid when we're doing an implant. Now, 3D printing, with the benefit of some really good medical imaging that has progressed a very long way in recent times. And it was really good to hear a radiologist's perspective earlier with Andy. But it's really the progression of medical imaging being really good quality, very high fidelity, which means that now we can move on and create implants that are personalized. So what I want to do is take you through, again, like I said, the story of what's happened in Australia. So I'll take you through a couple of case studies, and I've got these all pictured here. And I'm going to end up by talking about a project that we're currently working on at RMIT. So getting straight into it, I just want to introduce you to this guy called Len. So Len lives in my home state of Victoria. Unfortunately, he had a cancer of the calcaneus. The calcaneus is a heel bone. So it's literally the bone that you stand on when you're walking or upright. The only treatment for a cancer of the calcaneus is to remove the calcaneus bone entirely. So that's your entire heel bone that a surgeon has to remove. What that means is you can't walk, and actually the treatment currently for cancer of the calcaneus is an amputation below the knee. So it's a pretty drastic outcome for someone with cancer of calcaneus, which Len had. Luckily for Len, he was seeing Professor Chung at St. Vincent's Hospital. He was under his care. And Professor Chung had a relationship with a company called Anatomics. And they talked and said, well, you know what, we can actually think about 3D printing an implant instead. So contact was made with the CSIRO, who had an electron beam printer. And between Anatomics and CSIRO, they were able to come up with an implant design. Now, a lot of the design work was done on the Anatomics side, but where CSIRO came in was is having the knowledge and the know-how around the EBM printing process. Initially, this design up here, up the top, was the first one that was suggested. Unfortunately, that was a mesh size that was it was a mesh size that was very fine, and that was really to reduce the weight, keep the weight down. But what was found was that when you take that implant, printed in an EBM system where you're working with a sinter cake, it's actually really hard to remove the sinter cake from the implant when it's got that really fine structure, and especially when you're having to get right through to the middle of the implant and be able to confidently say, yes, we have removed all of the loose powder. So we were working under a very tight time frame in order to turn that implant around. So about 10 days actually from first contact to surgery, which, you know, given that you've got to design, iterate, print, sterilize, package, and then do surgery, that's a lot of steps to include all in one go. So anyway, this initial design was proposed, and what we decided to do instead was to go down the path of a risk reduction. So because we couldn't confidently say that all the powder was removed, instead this design down here, down the bottom, was the one that was used in the end. So just to explain a little bit about this implant, you've got a reticulating surface here, which is highly polished. That's the surface that the bone, the healthy bone, butts up against. And you've also got attachment points, here and here for the Achilles tendon and the ligaments going down to the foot. For this implant, there's some structural stems across the middle here and then through there. And then the rest of the implant is what you see here, which is this holy structure. And that's just literally like, you could have effectively done drill holes through the implant. That's sort of how basic it was. But it was really, like I said, to risk reduce with regards to powder removal, which is really important when it comes to custom implants like this. And also to lightweight the implant, obviously. Titanium is heavier than bone. Having a very heavy heel wouldn't have been very comfortable. That implant went into surgery. Professor Chung was able to remove the calcaneus with the tumor in it, and said that the implant that was designed just slotted in like a puzzle piece. So sewed up, and Len was back on his feet and had a really successful rehab. So it was a really great outcome. What's interesting about this is that there was a lot of really good work in lattice design happening at the time at RMIT. And RMIT looked at the implant design, which obviously was done in a bit of a rush, and said, hey, we could apply some of our knowledge and experience in lattice design to medical implants, and was able to come up with this alternative design here at the top, which was a lattice structure design. So I'll talk a little bit more about those lattice structures. I think just to conclude on Len, who, despite what he looks like in this photo here, was actually very happy. This one was a one-off. So calcaneus, cancer of the calcaneus is very, very rare. And I don't believe that there's been another, this was sort of a world first. And I don't believe there's been another calcaneus bone 3D printed since then. I could be corrected on that, but certainly for anatomics, it hasn't been done. So, you know, it very much a one-off. A lot of design and engineering work has gone into this, a lot of prototyping work. As far as the cost of the total procedure, I don't know that, but, you know, the printing and the material was like a fraction of the overall effort that went into this. So moving right along, again, this is an anatomics and CSIRO collaboration with a hospital in Spain. This man had a chest wall sarcoma, so a very large tumor on his chest. Tumors, when they can be quite aggressive, can eat away at bone. And this left this man with basically hardly any chest wall, and then a candidate for this kind of very unique implant. So this one we produced here was also on an electron beam printer. You can see that we've gone through that same lightweighting, pretty crude approach of just putting the holes into the more solid bits of the sternum. One thing that was really interesting, I guess, innovation here, and this is what 3D printing allowed us to do, was the development of these tulip cups at the ends. Is what they were called, tulip cups, because they sort of look like tulips, but basically they fitted over the rib, and then a screw went from top to bottom and fixed down into the bottom. So the normal treatment for this is a plate and screw implant, and the issue with the chest is obviously breathing. You're talking and you're moving around, so the implant can come loose, and you can get screws even falling out in some cases, and it requires then a revision surgery, which is really the last resort that you want to go to. So with this type of style of implant, it's very securely fixed in place. What was cool about this is obviously you've got all the patient data, and you've got the implant design, and you can also produce, of course, the cutting guide for the surgeon. So the implant and the cutting guide gets shipped like that. When it came time for surgery, the surgeon just notches on that cutting guide, makes all these cuts down the ribs, and again, the report back was the implant worked perfectly. It was a perfect fit, and you know, a successful outcome again for that patient. Now, what's interesting about this is how anatomics has approached sternum implants. So unlike the heel, which was very much a one-off, the sternum has actually been done a few times since then, so at least in publicized cases. So I've got an example down here of probably the latest version of their sternal implant, and you can see that there's this white material over the top, which again is another, not 3D printed unfortunately, but it's a material called Polestar, and they use that as for things like facial implants. Basically it's a soft material, and it means that particularly with the sternum being where it is very close to the skin, you're not really feeling like Iron Man when you have this implant inside. So next on, I'm going to talk about, again, another collaboration with anatomics, this time with RMIT University. So remembering that heel with the lattice structure, anatomics said, well, you know, let's think about an implant where we think we can apply the lattice structure and use it actually in a patient. This lady is called Amanda. She was born with a congenital defect in one of her vertebrae. So it was malformed and leads to an uneven posture, which over time and over many years leads to a lot of pain. So Amanda was actually in immense pain and very much needed to undergo surgery for her spine imbalance. Because of the nature of her spine being so unique, 3D printing really was the best option. In this case, RMIT was able to take that lattice design knowledge and apply it to the implant design. The implant itself was designed to withstand 6 times the body weight. So a lot of pressure on that implant, and the lattice structures did a really good job of making a very lightweight implant, but very strong, but also matching the stiffness of the vertebra. It was said that the surgeon had actually had a standard off-the-shelf implant that he would have used instead if this one didn't work. But to have done that, he would have had to have removed a significant amount of bone, which is, again, not what you want to do. But thankfully for Amanda, when the surgeon came to surgery, he said that the implant fitted in like a lock and a key, basically slotted right in. And so time and time again, we always get these reports about how did the implant perform in the surgery, and it's always like it was a perfect match. So a really great outcome. Amanda was up and walking within 5 days and actually went on to carry a successful pregnancy. So a really nice story there. So moving on, this time still at St. Vincent's Hospital, which has been really a big leader in this field. But this one was a collaboration with University of Melbourne. So this man is Richard Stratton. He had a malformed jaw from a knock he'd received as a child. And the issue with the jaw is that, a little bit like dental records, jaws, faces are very, very personal. And it's very hard, you know, no one human face jaw dental record is unique. And so this particular implant, it's called a TMJ, a temporomandibular joint. And there are definitely more conventional options here that are available that you can use. The issue with the jaw is that you have a very limited amount of bone stock to work with. So if you can produce an implant that's very strong, but also very small, then that's great. The jaw is subject to a lot of different forces. So, you know, in the course of a day, you are eating, you are talking, and you also might be grinding your teeth at night or clenching down. There's a very diverse range of forces that need to be accommodated for with that TMJ. So the University of Melbourne, their biomechanics department, did extensive testing on this implant for Richard. I call it a Brad Pitt jaw because he joked, make me look like Brad Pitt. I don't know about that, but he certainly, the outcome was great for Richard. After the swelling had gone down, he was very happy. And most importantly, this isn't a cosmetic. I want to stress this isn't a cosmetic job. This is really a structural job. So Richard had a lot of pain in his jaw. Now, when you have a lot of pain in a jaw, that affects your ability to eat properly, which really affects your nutrition. And longer term is a real indicator of very, very poor health outcomes. So it's definitely one that to get it right makes a really big difference in quality of life. And obviously this guy's quite young, so very important here to be able to get that right. So yeah, going back, like I said, he experienced no pain after the surgery, once the surgery had settled down, and was really very happy. What's cool about this story is that this was very much a one-off. So kind of like the heel, very custom, very one-off. But what happened is that the George Dimitroulis, the surgeon who was behind this implant, then took this into a spin-out company called OMX Solutions. So OMX Solutions now makes TMJs. They make a product down here that I've got down here called an osseo frame, and they have a few other products. Very all around the craniofacial implants. And they have a whole business selling loads of these products, all personalized, eligible for reimbursement through private health insurance, importantly, and have very successfully scaled this from being a one-off into a company, a commercial enterprise, producing a lot of different products. But all at a sort of a mass customized basis. Software really, again, software is the key enabler here. Without software and the ability to standardize somewhat, it would be very, very hard to do this on a commercial basis. So, this was in 2016 when software at the time was much more readily available in this field of personalized implants prior to this. So, for example, like when the spine was done, software was not really kind of up to the job. So everything was very bespoke, very one-off. So this is very much the time when we start to see a little bit of an inflection point around personalized implants. And so last I want to finish on really the jewel in the crown as far as Australia goes with regards to personalised implants. And I actually believe globally is such a fabulous, fabulous project. So again, going back to those ladder structures that RMIT was working on and had done a significant amount of very deep work and analysis around ladder structures, and particularly as they relate to implants, orthopedic implants. Stryker, who I'm sure you're all familiar with, very, very large medical company, medtech company, global company, saw the work that RMIT was doing in these ladder structures and said, we want to take that, but we want to take it to scale. So how can we take that work to scale? So first of all, what that involved was rather than focusing on really unusual types of implants or very rare types of implants or rare cases, they said, you know what, the biggest market for this is actually, it's called a proxial tibia distal femur. It's this part of the bone either side of the knee. So it's just as the knee comes down and turns into a more sort of straight bone, and there's some growth plates around there. There's a lot of metabolic activity in those regions, and that's then it's not exactly known, but it's thought that that is the reason why there's a lot of tumors that actually grow around those growth plates because of the metabolic activity. So as far as orthopedic implants go, about 60% of orthopedic implants are in those zones, either side of the knee, tumors either side of the knee. So they said, we want to attack that market. And if we can prove out the protocols around this, if we can bed down the systems with implants in this region, then we can take it to other parts of the body. So really in this project, very focused on that part of the body. And also wanting to, so taking it to scale is focusing on a larger market segment, but also focusing on software development and also robotics. So Stryker is a real leader in robotic surgery, and they very much wanted to incorporate robotic surgery into this project. Just a little note, I want to talk about the ladder, go back to the ladder structures that RMIT is working on, because that's really what makes this very, very unique, this project. And so earlier when I was talking about the stiffness of an implant and how we really, for a successful implant, we really want it to be able to match the stiffness of the surrounding bone. Now, bone is basically composed of two types of bone, trabecular bone and cortical bone. So trabecular bone is not as stiff and in some cases very porous type of bone, whereas cortical bone is very hard. Generally speaking, so for example, if in this implant down here, down the bottom here, that's where you would find the trabecular bone. And whereas down here, that's where you'd find the cortical bone. So you want an implant that's less stiff up here and more stiff down there. And that's going to mean that bone here is going to be happy and bone there is going to be happy. Hopefully you can see my cursor to know what I'm talking about. But basically, as you head towards the knee, it's more trabecular in nature. And as you head down away from the knee, it's more cortical in nature. So what the team at RMIT and specifically Dapan has been able to do has been able to tune the ladder structures to match the stiffness of the implant to the bone. Really important innovation here. Now, with regards to the, and I suppose going back to the example of the heel, where we had big support stems there's no support stems in these implants at all. It is purely just lattice structure. So it's regarding the software though, because I think this is a really interesting point. The software that's being developed is it's sort of similar to many types of software out there at the moment for personalized implants. But what we have been able to do has been able to say, okay, go from patient data, an image, to implant design file generation. But what's important is the thing that happened in between those two, which is a whole lot of algorithms telling the design how the lattice structure should be placed, how it should be designed, such that all of that knowledge and information that we have on lattice structures and their stiffness and strength as they relate to bone. And in addition to that, also manufacturability. So these implants, when they're designed, are completely manufacturable. So they're not requiring any support structures, they're supportless. And I think this is an incredible innovation, because to be able to go from not only from patient data to design output, but design that has lattice structure that matches bone density, is biocompatible and is able to encourage bone to grow into it and be completely manufacturable, is a really amazing outcome. And so in addition to doing the implant design, also a whole lot of tooling, tool paths are generated as well for the robotic surgery. So when as a surgeon, you can do straight cuts like that at the top. They're pretty straightforward, but if you want to do a more conformal type cut, like the one down the bottom left, that's quite difficult. And actually for a human, sorry, the robots have got us on this one, humans don't do this very well. So when you can do this conformal cut, you're going to minimize the amount of healthy bone that you're removing. So remember, we want to try and leave as much healthy bone in the patient as we can. So using robotics, we can do this successfully.
Hey, Alex, let me interrupt real quick. We've got about 3 minutes left, and you've got a list of questions lining up. Would you rather finish?
I'm going to finish now. Yeah. So. Yep. So I think this is a really great example. Like I said, if we go back to the heel and how we started there, there is a real community of practice here in Australia around personalized implants. It's very much a case of a whole lot of cooperation, collaboration, as you can see, between universities, research institutes, private companies, both small and also very large. So thank you very much for listening to me, and please come and see us at floor 6, table 8 in the next networking session if I don't get to all your questions, which I don't think I will. Thanks.
Thanks, Alex. All right, let's try and get to at least one or two. So the first one, with fatigue properties still somewhat of a challenge when using lattices, how do companies ensure that lattice bars don't break off while in the body?
Yeah, that's what a lot of our research is about, looking very, very much in terms of lattices and how they fail, and ensuring that they're strong enough that they will withstand all of the forces that they would be subject to. So I think, what's I guess a reasonable point to make here is you have an implant that's in that zone around the knee. That's going to be subject to a certain amount of forces. It's going to be very different to, like I explained, the TMJ. So understanding what the forces are and then designing for them. And all I can say is, like, lots of research, big research team behind that.
That makes a lot of sense. Okay, so for the rest of them, Alex, we'll forward them to you so that hopefully they'll meet with you at your table at the next networking session. And we thank you very much for participating.
Lovely. Thanks so much for having me.
Thanks, Alex. Bye-bye.